Welcome to Tomorrow Unveiled. And welcome to Tomorrow Unveiled. We are doing a deep dive today into what our dedicated research team has identified as, well, a really pivotal moment, a genuine inflection point in the history of the global energy transition.
Yeah, it's not just about small gains, is it?
Right.
We're not talking incremental progress here.
Not at all. The period our team flagged that week between November 19th and 26th, 2025, it represented a real structural shift.
It was this concentrated burst of breakthroughs. You saw it in technology, in policy, and definitely in investment. It all just converged.
And it confirmed, I think, the future path for how civilization is going to power itself. So we're calling this the Green Code Hot Core Thesis.
It's a great way to frame it. For the last, decade, the conversation has been so focused on energy sprawl.
Right, covering huge areas of land with wind, with solar, the physical footprint.
Exactly, the sprawl. But the activity our research team captured this week, it confirms that the market and, strategic policy are shifting very, very quickly toward energy intensity.
And a big driver of that shift, maybe the biggest, is the soaring demand from next-gen infrastructure. I mean, we're talking about AI and data centers.
Oh, absolutely. The demand is just insatiable. They need reliability, first and foremost.
Massive continuous power. And they need it packed into dense, localized spots.
Which brings us to the thesis. Let's define the terms for everyone.
Okay, so the hot core side. That represents these high-density, always-on thermal energy sources.
We were talking about the heavy hitters.
Yeah, advanced nuclear fission for sure,
Yeah.
the commercialization of fusion energy, which we'll get into, and also harnessing superhot geothermal heat, deep inside the Earth.
All technologies that pack an immense amount of power into a really minimal contained footprint.
Then you have the other side of the coin, the green code.
And this is the great accelerator, the operational and the regulatory accelerator. It's this revolutionary change that's being enabled by, advanced digitalization.
So it's the use of highly sophisticated AI, these physics-informed machine learning models, complex digital twins.
Right. All being used to crack the absolute hardest engineering challenges in energy.
Like what?
Well, everything from managing plasma that's hotter than the sun to discovering new materials that can even withstand those temperatures.
And maybe most importantly, convincing regulators that these incredibly complex systems are actually safe and predictable.
That's the billion-dollar question, always.
So our mission today on Tomorrow Unveiled is to really unpack this convergence. We are looking at a future where this exponential demand for compute power is met by power generation that's moving toward intensity.
And it's all driven by these elegant, almost invisible solutions of the Green Code.
So the core question is, how fast is this future actually arriving?
Well, the converging evidence, and our team has pulled this from national labs, corporate boardrooms, federal agencies all over the world, it provides a really clear answer.
Which is?
Very fast. High-density clean energy is moving firmly out of the if category. It's not a question of if anymore.
It's now in the realm of how fast can we scale?
Exactly. This whole trajectory, it's not speculative research anymore. It's backed by strategic policy alignment and, frankly, unprecedented levels of private capital. The market signal could not be louder or clearer.
Reliability, minimal footprint, and density.
Those are the new premium assets in the energy world.
Okay, let's start at the absolute peak of that intensity pyramid. Let's talk about fusion.
Right.
For so many of our listeners, fusion has kind of been the punchline, right? The technology that's always 30 years away.
Always just over the horizon.
But the reports from our research team, just from this 1 week, show private companies hitting these fundamental physics and engineering milestones, things that used to be, the exclusive domain of these huge multinational government mega projects.
And that acceleration is the key. That's the real story. We're past the era of just proving the physics can work.
Okay.
The goal now is proving the engineering can scale affordably and reliably. And private capital, is driven by the urgency of this power demand. It's just iterating at speeds governments simply can't match.
We saw 3 huge announcements this week, right? All around different paths to making fusion a commercial reality.
3 major, distinct approaches, all hitting critical milestones at the same time.
Okay, let's unpack Tokamak Energy first. This is a UK-based company, and they achieved a world first that is fundamentally an engineering feat.
A huge engineering achievement.
Tell us about this magnetic milestone. Why does it enable smaller reactors?
So Tokamak Energy achieved what are called fusion power plant level magnetic fields. We're talking 11.8 Tesla.
Which is immense.
Immense. And they did it using a complete high-temperature superconducting magnet system, an HTS system they call Demo 4.
Right, the HTS technology, that's the key here, isn't it? Why does that change the economics and the engineering so drastically?
It changes everything. I mean, traditional fusion magnets, they rely on low-temperature superconductors or these just massive copper coils.
Right, big, bulky, expensive.
Exactly. But HTS technology, it uses materials like yttrium barium copper oxide, YBCO. This allows for roughly 200 times the current density compared to copper.
200 times.
Think of it this way. To generate that huge magnetic field, you can use a massive amount of copper, or you can use a tiny, minuscule amount of HTS wire.
So that current density lets you get stronger fields in a much, much smaller physical volume.
Precisely. And that allows the physical size of future commercial devices to be just dramatically shrunk.
Which cuts down on everything else: steel, concrete, construction complexity.
It makes fusion reactors potentially factory producible, instead of these massive custom-built facilities. In the fusion world, size directly equates to cost.
So that just dramatically lowers the barrier to entry. Okay, so shifting from the magnet engineering to the core physics, let's talk about Zap Energy.
A totally different approach.
They're pursuing what's called the Z-pinch, which is defined by its ability to get rid of those massive magnets entirely. What was the milestone they validated?
Zap Energy's device, the FuZi3, it achieved a record plasma pressure of 1.6 gigapascals.
Okay, put that in perspective for us. 1.6 gigapascals.
That is roughly 10 times the pressure you would experience at the bottom of the Mariana Trench. Just unbelievable pressure.
And they sustain that for how long?
About 1 microsecond, which it sounds short, but it's more than enough time to validate the confinement physics of their approach.
That is just an astonishing amount of localized pressure. So if they're not using superconducting magnets, how do they actually confine the plasma? How does that work?
Their approach is called sheared flow stabilized Z-pinch. It's clever. Instead of relying on these huge external magnets, they use the plasma's own powerful magnetic field to confine and compress itself.
But the historical problem with the Z-pinch was instability, right? The plasma would just wiggle and break apart.
Exactly. It was notoriously unstable. What Zap does is they use a third electrode in their FuZi3 device that creates what's called a shear flow. It essentially spins the plasma so fast that it keeps it stable.
So achieving that record pressure validates that a magnet-free, super-compact pathway to fusion is actually achievable.
Yes. It shows the incredible diversity of this hot core movement. It's not just one technology that's going to win. It's multiple dense approaches succeeding at the same time.
And that brings us to the third one, TAE technologies. They're known for their field reverse configuration, or FRC, and they made a really significant strategic announcement.
An announcement that, it speaks volumes about their confidence in these recent breakthroughs.
They said they're going to skip their planned 6th-generation device entirely.
That's right. They were planning a machine called Copernicus. They're skipping it. They're going straight to Da Vinci, which is their first commercial power plant prototype.
And they're targeting the early 2030s for that. Skipping an entire generation of development in advanced energy is a massive declaration.
Almost unheard of.
What specifically enabled them to do that, to leapfrog years of R&D?
It was a breakthrough in plasma formation on their existing machine called Norm. They achieved a stable FRC plasma, that's that characteristic sort of smoke ring shape, at over 70 million degrees Celsius. But here's the key. They did it using only neutral beam injection, or NBI.
And that was the goal for decades, right? To get rid of the old formation method.
Exactly. Historically, to form that plasma ring, you needed these violent magnetic theta pinch coils.
So what was the engineering nightmare with those theta pinch coils that using NBI now eliminates?
Well, the theta pinch coils, they required these massive instantaneous energy dumps. Think of it like a sudden lightning strike inside the machine.
Okay.
That demands enormous specialized capacitors and just incredibly robust structural integrity to handle the immense mechanical forces from that pulse. It made the machine mechanically complex, hard to maintain, and unbelievably expensive.
So by eliminating those coils and using this cleaner, more sustained NBI process,
they can potentially reduce the overall length and complexity of the reactor by up to 50%.
Wow.
And that simplification, it dramatically reduces the capital cost, and it increases the theoretical reliability you need for continuous commercial operation.
So we're seeing engineering innovation with Tokamak, physics validation from Zap, and now streamlined complexity from TAE. It's all converging.
And it's not just private industry on offense here.
Right. The U.S. government also signaled a pretty profound institutional shift this week to support this commercialization timeline.
Yeah, the U.S. Department of Energy announced a major reorganization. They've created a new standalone Office of Fusion.
And the key is where it sits in the bureaucracy, isn't it?
That's it. Critically, this new office reports directly to the Undersecretary for Science. This separates fusion from the purely academic, research-oriented mission of the broader Office of Science.
So what's the consequence of that elevation in practical terms?
It formalizes the government's commitment to commercialization. It's a clear strategic signal that they want to accelerate this technology's path to market.
And maybe most importantly, it's about regulation.
Yes, it facilitates rationalizing the permitting process and establishing clear licensing frameworks. Up until now, fusion had no clear regulatory home.
So this new office will work directly with the Nuclear Regulatory Commission, the NRC, to actually build a framework for licensing these future devices.
Which is absolutely essential. Without a clear regulatory path, no commercial enterprise can move forward. Doesn't matter how great your physics is. This instituting your move, it validates all the accelerating private sector progress we just talked about. It's preparing the regulatory environment for what's coming.
Okay, so if fusion is the, let's call it the ambitious long game, then advanced nuclear fission, specifically small modular reactors, or SMRs, that's the immediate scalable solution driving the hot core thesis today.
Absolutely. Our research team's analysis confirms that SMRs are moving incredibly fast. They're going from the concept and licensing phase right into massive capital formation, supply chain scaling, and fulfilling actual orders.
The transition from a paper design to a real infrastructure asset is happening right now.
It is. And the central narrative this week really belonged to X Energy. They're making that jump from being a design firm to a full-fledged industrial energy manufacturer.
And let's start with the financial confirmation of this. X Energy closed an incredibly substantial funding round.
They did. An oversubscribed $700 million Series D funding round.
Oversubscribed, so more people wanted in than they could even take.
Exactly. And this financing was led by some really high-profile funds, Jane Street for one, with major participation from institutional players like Ares Management and ARK Invest.
And that single injection brings their total capital raise to over $1.5 billion.
That amount is just monumental. It is one of the largest private capital injections into advanced nuclear history.
So for the listener who hears $700 million, what does that investment functionally signal to the market, especially coming from tech-aligned funds like ARK? Are they just betting on density?
They're betting on commercial certainty, and they're betting on the demand profile of the future economy.
Right.
For a company like Amazon, which is a confirmed X Energy customer, density means a few things. It means faster site approval because the footprint is tiny.
Lower transmission costs, I'd imagine?
For sure, because the plant can be sited right next to the data center load. But most importantly, it's the guarantee of 247 firm, dispatchable power that intermittent sources just cannot offer.
So this funding really validates that Wall Street now sees SMRs as a critical near-term infrastructure asset, essential for powering things like AI training and data centers.
And that market confidence has translated directly into a massive, tangible order book. They have confirmed anchor customers.
What does that order book look like?
It's huge. X Energy now holds an order book for 144 SMRs. That represents a substantial 11 gigawatts of capacity.
And the customer list itself confirms the strategy, right?
Absolutely.
Okay.
Confirmed buyers include a tech titan like Amazon and an industrial behemoth like Dow Chemical.
And their first commercial deployment is specifically targeting Dow's facility in Seadrift, Texas in the early 2030s.
That's the plan.
So why is their reactor, the X100 SMR, so attractive to these big industrial players, especially Dow? It goes beyond just making electricity, doesn't it?
Oh, it absolutely does. It comes down to utility and the kind of power they produce. The X100 is an 80-megawatt electric, high-temperature gas-cooled reactor.
Okay.
Critically, it produces process steam at extremely high temperatures. We're talking up to 565 degrees Celsius.
Which traditional nuclear reactors don't really do. They're mostly just for electricity.
Exactly. But heavy industries, chemical production, cement manufacturing, steel fabrication, they require enormous amounts of heat. The X100's high-grade heat is perfect for both clean electricity generation and for replacing the fossil fuels they use for that industrial process heat.
Which is a huge part of decarbonization efforts.
A critical part. This dual-purpose capability just significantly broadens the market for SMRs way beyond the electricity grid.
But of course, you can't build 144 reactors without a reliable, scalable fuel source. Our research team highlighted a critical development on this front, the TrizoX facility.
This is, you could argue, the most crucial physical supply chain development we saw this week. It validates the entire commercial model.
So construction began on this facility, the TrizoX TX1 in Oak Ridge, Tennessee.
That's right. And this will be the first U.S. facility manufacturing fuel exclusively for these advanced SMRs. It's going to produce these robust, meltdown-proof TRISO fuel pebbles.
Okay, we hear TRISO fuel a lot. Let's expand on its importance for regulation and for public confidence. What does meltdown-proof functionally mean in terms of its design and safety?
It's the key. It's the key to minimizing the chance of a Fukushima-style incident, which in turn provides regulatory stability and public confidence.
Right.
TRISO fuel isn't metal rods. It's these poppy seed-sized particles of uranium, and each one is coated in layers of carbon and silicon carbide.
So it's like a tiny, self-contained pressure vessel.
That's a great way to think of it. The shell is so robust that it retains all the fission products, even at extreme temperatures, far, far beyond normal operating conditions.
And the reactor itself is passively safe.
Yes, the X100 design is passive. It uses helium coolant and physics itself to prevent overheating. Even in a worst-case scenario, the fuel retains its integrity. The fact that the NRC is moving so quickly to approve this TX1 facility, that shows they are fundamentally comfortable with this accident-tolerant fuel paradigm.
And what's the timeline payoff for this facility?
When TX1 is operational in 2027, it will be able to supply enough fuel to sustain up to 11 X100 reactors annually. It immediately tackles that critical fuel supply bottleneck.
It basically turns X Energy into a vertically integrated energy solution provider.
Exactly. They control the design, the build, and now the fuel supply.
And beyond X Energy, we're seeing this acceleration being driven by other factors too. Military necessity and some sharp international competition.
Yes, the U.S. Army officially launched what they're calling the Janus program. The target is to install microreactors, which are just small-scale SMRs in the 1 to 20 megawatt range, at a military base by 2028.
And that's about secure off-grid power resilience for them?
For them, yes. But for the civilian market, it serves as this crucial fast-track test case for rapid standardized deployment and, streamlined regulatory approval. There are huge synergies with future civilian data centers and community microgrids.
And of course, the competitive pressure from China is undeniable.
Oh, the global race for nuclear supremacy is absolutely on. China's ACP-100, they call it the Linglong one, it just completed its cold functional tests.
And it's scheduled for commercial operation in 2026?
2026. This puts China on track to launch the world's first land-based commercial SMR. And that creates intense competitive pressure on Western timelines. It just underscores the speed at which this technology is maturing globally.
If you're finding it insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this rapid shift toward high-density energy. Does this focus on atomic power solve the immediate climate challenge, or does it introduce new complexities?
All right, let's pivot now to the second pillar of our thesis. This is the green code. This is where artificial intelligence, machine learning, and these advanced computational tools, they become indispensable partners to the hot core.
Yes. They're not just optimizing things. They are fundamentally accelerating material discovery, ensuring real-time reactor control, and I think most importantly, they're accelerating that slow, expensive process of regulatory approval.
This is the moment where energy R&D really moves from being this iterative physical process,
spending years building and testing prototypes,
to a computational in silico process. You simulate, you optimize, and then you build once.
And the U.S. federal government really crystallized this shift this week with a profound national strategy.
The launch of the Genesis mission. Explain the scale of this initiative for us.
The Genesis mission is a major executive order. It establishes an AI-driven science acceleration initiative, and it's being led by the DOE Undersecretary. The explicit goal, and it's audacious, is to leverage the National Lab System's supercomputers and AI infrastructure to double R&D productivity within a decade.
Doubling R&D productivity through AI. I mean, that's essentially formalizing what you could call computational energy policy. What does this mean for the hot core technology specifically?
It means the federal government believes that the path to the next generation of materials, or the next stable fusion regime, or the next reactor design, it doesn't require another multi-billion-dollar physical experiment.
It requires a better algorithm running on better hardware.
Exactly. And advanced nuclear, fusion, and grid modernization were explicitly prioritized in the mission. It's a profound strategic shift. It acknowledges that these computational tools are now the primary engine of discovery. They're solving the physical limitations of high-density energy before a single piece of steel ever touches the ground.
Let's look at a concrete example of the green code in action. Fusion control.
A perfect example.
You have to control plasma that's hotter than the sun for sustained periods. That's fundamentally an impossible task without AI, isn't it?
It truly is. It's a real-time problem that no human could ever solve. A collaboration using what's called machine learning for heat flux, or heat ML, they demonstrated a breakthrough in plasma exhaust management.
So they can predict and identify safe zones for the plasma exhaust system, the diverter, in just milliseconds.
Milliseconds.
Why is that difference, milliseconds versus, say, minutes? Why is that the difference between a research experiment and a commercial power plant?
Because when that superheated plasma hits the diverter plates, it can cause catastrophic damage. It can literally melt the physical hardware of the reactor.
Okay.
And calculating the heat flux, predicting the plasma's behavior, using traditional physics simulation codes, that typically takes up to 30 minutes.
So if the plasma destabilizes in that 30-minute window, your reactor is severely damaged.
You're in big trouble. AI cuts that calculation time down to milliseconds. And that speed allows for an active real-time feedback loop. The superconducting magnets can adjust thousands of times per second, constantly correcting the plasma's position.
So the AI is essentially flying the plasma.
That's the term they use. It's continuously flying the plasma, making sure it stays stable and doesn't destroy the machine. This real-time, instantaneous control is absolutely non-negotiable for commercial viability.
So that's AI solving the operational difficulty. Now, how is the green code being applied to the more immediate SMR sector? Specifically, how does it tackle the massive soft costs of regulatory compliance?
This is where computational policy provides massive economic leverage. X-Energy uses a physics-informed AI simulation called SimuPact.
And this acts as a comprehensive digital twin, a perfect model of the reactor.
Exactly. It perfectly models the neutronics and the thermal hydraulics of the S100 reactor in real time. It's a virtual copy.
So how does that simplify the incredibly rigorous licensing process that's overseen by the NRC?
The regulatory advantage is immense. Historically, to prove a reactor's safety, you needed expensive, time-consuming physical tests and these lengthy conservative analyses.
Right.
SimuPact allows X-Energy to prove its safety cases, like modeling a severe accident scenario, say a loss of coolant event using simulation data that is demonstrably physics accurate, just faster and cheaper than physical prototyping.
But what about the validation risk? If the industry starts to rely too heavily on a tool like SimuPact, are we trading physical redundancy for digital efficiency? How is the NRC handling that completely new risk profile?
That is the critical question, and the NRC is actively addressing it. They recognize that simulation, as long as it's verified and validated rigorously, can actually provide deeper insight into a wider array of failure scenarios than physical tests ever could.
Okay.
So the NRC is accepting these digital safety cases because the models are what's called physics-informed. They're built on verified scientific principles, not just empirical data.
And this speeds up the process, reduces their soft costs, the time, the paperwork, which has historically been one of the biggest barriers to nuclear deployment.
That's it. The Green Code is essentially reducing risk and accelerating timelines by allowing the industry to build in silicon before they ever commit to building in steel.
We've established the atomic core fission and fusion and the computational acceleration of the Green Code. Now we can turn to the third component of the hot core thesis, which is deep Earth energy.
Right. Let's talk about superhot rock geothermal. This is about harnessing the relentless, always-on thermal core of the planet itself.
Geothermal is often thought of as a niche technology.
It has been, but it's undergoing a real renaissance right now, and it's leveraging all the advanced drilling and subsurface techniques that were perfected over decades by the oil and gas sector.
And this week saw a major step forward in what are called enhanced geothermal systems, or EGS.
A really big step forward.
What was the specific breakthrough that Mazama Energy achieved?
Mazama Energy achieved the world's hottest full-scale EGS pilot. This was at the Newberry volcano site in Oregon. They successfully circulated a working fluid at temperatures exceeding 300 degrees Celsius.
And that's not easy to do.
It's incredibly difficult.
All right.
It required successfully aligning a producer well with an injector well over 2 miles deep. And they had to use proprietary stimulation technology to maintain these complex heat-transferring fractures in incredibly hot, abrasive rock.
Reaching 300 degrees Celsius is monumental for EGS. What technical barriers does that break down, and what's the economic payoff?
Well, it establishes a viable commercial pathway to what are called superhot rock, or SHR, regimes. We're talking about temperatures over 400 degrees Celsius.
The engineering challenge there must be immense.
It is. The high temperatures increase corrosion, the stress on drilling equipment, the risk of the fractures collapsing. But if you can solve those problems, the payoff is huge.
How huge?
SHR could deliver up to 10 times greater power density than conventional geothermal, and it could potentially enable energy costs below 5 cents per kilowatt hour.
And that's 247 baseload power from, theoretically, any location globally where you can drill deep enough.
Exactly. It radically changes the siting availability for high-demand infrastructure like data centers.
And we also saw momentum from Fervo Energy this week, reinforcing this aggressive push into subsurface science.
That's right. Fervo secured over $200 million in financing, and they drilled their deepest, well, yet over 15,700 feet deep at 520 degrees Fahrenheit, which is about 271 Celsius.
So these are not small research projects anymore?
Not at all. These are multi-million-dollar aggressive commercial drilling campaigns aimed at proving that deep geothermal is a viable, firm power source capable of very rapid scale-up.
Okay, so the hot core technologies provide the baseload. But to stabilize the grid and manage the instantaneous power swings that are required by AI, we need high-density advanced storage.
You absolutely do.
What were the breakthroughs that defined the storage sector this week?
We saw crucial advancements in two really distinct storage categories: short-duration, high-density batteries on one hand, and long-duration, high-resilience systems on the other.
Okay, let's start with the short duration.
For that, LG Chem in South Korea announced a significant breakthrough in solid-state batteries.
Tell us about the importance of achieving uniform solid electrolyte particle sizing. It sounds very technical.
It's a microscopic engineering detail, but it directly addresses the primary challenge in commercializing solid-state batteries, which is internal resistance and capacity fading over time.
Right.
By achieving this uniform particle sizing, LG Chem delivered roughly 15% higher energy capacity and 50% greater high-rate discharge capacity than current liquid lithium-ion cells.
And that's essential for high-performance EVs, but also for grid storage, right?
Critically for grid storage, you get the necessary energy density and safety improvements you need for massive centralized grid storage systems, and you eliminate the flammable liquid components.
And then for the long-duration needs of industry and data centers, we saw flow battery technology maturing rapidly.
Yes. Flow batteries, specifically vanadium redox systems, or VRFBs, they're emerging as a core solution for applications that require 10 to 100 hours of continuous discharge.
And our research team highlighted a company called Terraflow Energy. They're developing these batteries as power filters for AI data centers.
A power filter. It's a great description.
Elaborate on that specific industrial role. What does that mean?
It addresses the instantaneous volatility that's inherent in large computational infrastructure. When a data center starts or finishes a massive AI training run, you can see power swings of dozens of megawatts per minute.
So the flow battery absorbs that swing.
Exactly. They use these stable, non-flammable, water-laced electrolytes, and they have a 25-year lifespan. They're ideal for absorbing that immense volatility and providing seamless, resilient power, protecting all that sensitive, expensive equipment.
And we saw this scale being validated with a large commitment from Terraflow for the Port of Victoria project.
A huge commitment. They're targeting 1 gigawatt of storage capacity, which just shows the massive industrial scale that's required for these high-demand zones.
And finally, let's not forget the simple, low-tech, high-density thermal sponges that also serve a vital role.
Yes. Polar Night Energy in Finland. They announced the construction of a 250 megawatt-hour sand battery.
A sand battery?
It uses simple, crushed soapstone and sand, often industrial byproducts, to store excess wind and solar heat up to 600 degrees Celsius in a big insulated silo. This heat is then fed into the local district heating network.
So what's the strategic function of a massive sand battery in this highly complex energy transition?
It demonstrates that high-density solutions don't always require cutting-edge chemistry. It offers over 5 days of discharge duration, and it acts as a massive thermal sponge.
It doesn't produce electricity back to the grid, though.
No, but it decarbonizes the massive demand for heat. And by using simple inert materials, it frees up all that electricity generation capacity that would otherwise be used to heat buildings, reserving that valuable electron flow for the grid and for high-demand applications like data centers.
Okay, so the technical breakthroughs we've discussed, the fusion acceleration, SMR capitalization, geothermal density, none of this is possible without a fundamental shift in policy and investment priorities.
It's not at all. Governments and financial markets are now explicitly prioritizing watts per square meter, Willamore, or power density as the new metric of success.
And that prioritization was essentially codified this week by a critical U.S. policy change, the capacity density doctrine.
Right.
Tell us about the U.S. Department of the Interior's Secretary's order. How does it functionally change what gets built on federal land?
This order from the Department of the Interior, it fundamentally reshapes how energy projects are assessed and permitted on these massive tracts of federal land. It now requires prioritizing projects based on capacity density.
So explicitly favoring sources that generate the most power per acre.
Exactly.
And federal lands are precisely where these massive, sprawling solar and wind projects, the energy sprawl we talked about, are typically sited, especially in the U.S. West. So what's the immediate practical implication of this shift?
The immediate implication is that this move imposes a severe new regulatory hurdle on large, land-intensive solar arrays and extensive wind farms on public lands.
And the stated rationale for this?
The stated rationale is that advanced nuclear and geothermal are far more efficient in their land use, which aligns conservation goals with energy efficiency. This doctrine signals a very clear preference for SMR siting, for advanced geothermal drilling, and related critical mineral mining.
So it's favoring high-density sources that minimize habitat fragmentation. It's a formalization of the hot core thesis at the federal policy level.
It really is.
And alongside this land use mandate, we saw the DOE reorganize its structure, which is always a strong signal about where federal capital is moving. This reorganization included some pretty significant funding cuts to existing programs.
That's right. In addition to creating that new prioritized Office of Fusion, the DOE took the strategic, though definitely controversial, step of dissolving several clean energy offices,
including the Office of Energy Efficiency and Renewable Energy, and the Office of Clean Energy Demonstrations. Our research team noted that this has potentially massive financial implications. Reports suggest nearly $24 billion in previously announced awards might face cancellation, including over $10 billion in clean energy funding cuts reported this week alone. Does this shift risk killing successful, smaller efficiency programs for the sake of these long-term nuclear bets?
And that is the core risk. That's the short-term negative externality of this policy consolidation. ERA managed a lot of successful efficiency programs that provided near-term consumer savings.
Right.
However, the strategic calculation appears to be that the long-term structural need for firm, dense power outweighs the incremental gains of these decentralized efficiency programs. The signal is just unambiguous.
The federal government is redirecting focus and capital toward the scale-up of firm, high-density power SMRs, Fusion, the Genesis AI mission, rather than continuing to fund a broad portfolio of variable or small-scale solutions.
It is a strategic consolidation of focus and of capital.
And finally, the hot core transition really became a strategic foreign policy tool this week, which confirms its geopolitical importance.
This was confirmed by two major institutional moves. First, the U.S.-Saudi Arabia Joint Declaration on Civil Nuclear Cooperation.
This established a critical framework for a multi-billion-dollar, decades-long partnership.
And the aim is explicit: to make U.S. companies the partners of choice for Saudi Arabia's future nuclear program. This is about securing geopolitical influence, it's about establishing U.S. non-proliferation standards globally, and crucially, it's about securing a future customer base for U.S. SMR and advanced fission tech against competitors like China.
And internationally, we saw a landmark institutional endorsement of nuclear power from the financial community.
Yes. The Asian Development Bank, the ADB, and the International Atomic Energy Agency, the IAEA, they signed a landmark agreement.
And this is a major policy shift.
It's huge, because the ADB, which controls massive infrastructure financing in emerging economies, now officially recognizes nuclear power as a viable, crucial alternative to fossil fuels for baseload generation.
So this agreement supports safe and sustainable nuclear energy development in the Asia-Pacific region, giving emerging economies access to crucial financing and expertise.
And proper safeguards. It signals the global financial community's acceptance of advanced nuclear as an essential tool for clean power, and that unlocks trillions in potential infrastructure investment.
Okay, we've covered the breakthroughs, the policy, and the investment. Now let's tie it all together. Let's connect this hot core green code density theme to its fundamental real-world impact.
On sustainability, on land use, and on these rapidly compressing commercial timelines.
The foundational sustainability argument for this pivot seems pretty stark. It's the land use distinction.
It's unassailable, really. If civilization has to rapidly decarbonize while meeting the surging demands of AI, then minimizing the physical footprint of our energy infrastructure is a primary constraint.
Our dedicated research team provided some essential, non-negotiable figures here. We should use some specific data points to show the listener the sheer magnitude of the difference between density and sprawl.
Let's use power density. Measured in watts per square meter, William, it's the metric the Department of the Interior is now prioritizing.
Okay.
Nuclear energy, being inherently dense, achieves approximately 1,000 watts per square meter of power output.
1,000. And compare that to utility-scale ground-mounted solar PV.
Solar sits at around 100 watts per square meter, and onshore wind is significantly lower, down to maybe 2 or 3 williams more when you account for the necessary turbine spacing and exclusion zones.
So that's a fundamental tenfold difference between nuclear and solar, and it's exponentially larger compared to wind. What does that mean for real-world land consumption?
It leads to these radical differences in land requirements. The data shows that a 1,154 megawatt nuclear plant can require 170 times less land than an equivalent output from a wind farm.
Even factoring in the different capacity factors.
Yes, even accounting for nuclear's 92.5% capacity factor versus the lower factors for renewables.
Okay.
And crucially, high-density power drastically minimizes material intensity.
Less steel, less concrete, fewer critical minerals per unit of energy.
Exactly, and it alleviates the need for massive new transmission corridors to haul power from these remote sprawling sites to population centers. That reduction in transmission is a huge, often overlooked secondary land use benefit.
Beyond land, the other critical factor driving this hot core adoption is the reliability factor, particularly as the demand for continuous AI computation grows.
Correct. Nuclear energy maintains the highest capacity factor of any energy source globally at 92.5%.
It's generating near maximum power, virtually 247.
Making it nearly 3 times more reliable than variable sources like wind and solar. And the IEA Renewables 2025 report, which our research team analyzed, it documents these mounting grid integration challenges for variable renewables.
Like rising curtailment, which is wasted energy, and increasing negative pricing hours.
Right. These challenges just highlight the critical immediate need for the firm, dispatchable 247 power that the hot core technologies are specifically designed to provide for both industrial use and grid stability.
I think the most exciting conclusion from this week is how rapidly these commercial timelines are converging. It's putting these dense technologies on a collision course with the energy demands of the early 2030s.
The pace of commercialization is just startling.
Let's run down the commercial targets our research team noted.
For SMRs, China is targeting commercial operation of its Linglong 1 SMR by 2026.
2026.
Here in the U.S., X Energy and TerraPower, with its Natrium fast reactor, they're targeting deployments in the early 2030s. These are firm, funded deadlines.
And fusion has clearly moved beyond being just a science project.
Oh, absolutely. The private fusion industry has drastically accelerated its ambition. At least 35 of the 45 companies in the sector now anticipate operating commercially viable pilot plants between 2030 and 2035.
Helion, backed by that Microsoft power purchase agreement, they're targeting 2028 for their 50-megawatt Orion plant.
And Commonwealth Fusion Systems is targeting a net energy demonstration in the late 2020s, with a commercial plant in the early 2030s.
And even Superhot Geothermal is moving faster than expected.
Fervo Energy's Cape Station Phase I, that's a 100-megawatt project. It targets 2026 operation, and they have plans to rapidly scale up to 2 gigawatts of capacity.
So the combined activity this week proves these timelines are transitioning from just aspirational goals to funded engineering projects.
They are.
But every massive industrial shift has a critical bottleneck, something that can halt or slow down momentum. What's the primary challenge moving forward for the nuclear segment that our research team identified?
The primary challenge is the supply chain, specifically uranium. The World Nuclear Fuel Report 2025 analysis noted that current global mine production only covers about 90% of current reactor requirements.
And there's an even bigger crunch in the next step, right?
Yes, more critically, the conversion services, that's the necessary industrial step before you can fabricate the fuel, are described as very tight in the near to midterm.
So if this new wave of SMRs comes online in the 2030s without coordinated multi-billion-dollar investment in mining and conversion infrastructure today,
This constraint could severely limit capacity growth. The next major challenge, after solving the reactor design, is securing the fuel.
if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this green code hot core transition and what you believe is the single most critical breakthrough discussed today.
So, to summarize this pivotal week, we saw the convergence of fusion acceleration, with private companies achieving milestones that drastically shrink reactor size and complexity.
Massive SMR capitalization, driven by X-Energy's $700 million funding round from tech-aligned firms who are betting on density.
We saw critical AI integration through the Genesis mission, which is essential for safely and efficiently managing these hot cores.
And a sharp policy shift toward density over sprawl, codified by the Department of the Interior.
That convergence confirms that high-density clean energy is transitioning to commercial reality much faster than expected, and it's being driven by the uncompromising power demands of the digital economy.
The ultimate consequence of this green code hot core thesis is that the energy transition will be defined less by how much land we must sacrifice and more by how intelligently we can manage extreme temperatures and atomic forces.
So we're betting on ingenuity over acreage.
Exactly. The question you need to consider now is, how quickly will your local grid or your industrial base adapt to this new priority of power density? Will the next major data center built near you run on sprawling wind farms stretching for miles, or a microreactor the size of a shipping container providing firm 247 power?
The policy and the capital flows from this week suggest the latter is rapidly becoming the favored path to tomorrow.
It certainly does.
Thank you for joining us on Tomorrow Unveiled.